So hello, so it's my pleasure to have Chee Yap from the Courant Institute at NYU speaking for us about effective isolation of real simple zeros of system of equations with complexity analysis.
Thank you, Remy. So, I guess the term that I'm using here, effective, needs a bit of explanation. Isolation, we know we want to isolate roots. That is, for each root, we need a box that contains a single root, and not more than one, and not zero, for instance. And we are interested in the real case, and we talk about systems of equations, not necessarily polynomial. Okay, and we'll do some complexity analysis for this. This is joint work with Joan from Beihang University. So this is a very classical problem of solving systems of equations, say f1 to fn in n variables, x1 to xn. So it's a square system. And the techniques that you use to solve such a system depend greatly on, first of all, whether you're talking about zero-dimensional system, and we are. Because if you have non-zero dimensional system, you're talking about, say, one-dimensional system, you're tracing a curve or tracing a surface or hyperplane or whatever, and that requires different techniques for solving those problems. And whether you're talking about real or complex, and we are talking about real, because again, the primitives are very different, and whether you're talking about algebraic polynomials or analytic functions. And our technique here today will be applicable to analytic functions as well. And I want to emphasize on effectivity because this is a concept that I think people seem to miss until they start to implement, and then they realize they cannot implement what they describe as an algorithm. And traditionally, effective means it's Church-Turing computable. You can actually implement it on a Turing machine. But unfortunately, most algorithms about real numbers and complex numbers are described in a real RAM model where everything is algebraic operation and is exact. And to convert that into an effective algorithm is highly, highly non-trivial. Yes?
So you mentioned techniques depend greatly on those ingredients. How about the definition? So what is the meaning of solving?
Right. There are different meanings for solving. For the case of root isolation, we want boxes that contain exactly one root.
And if you have a non-zero dimensional system?
Non-zero dimensional, then you have to set some notion of typical way to do it is to approximate it by, let's say, a piecewise linear surface of variety. And you can control the Hausdorff distance between the real thing and what you do. Yeah, you have to make that clear in every case because real numbers, we cannot get access to real numbers. We have to access them through approximations. Okay, so there are three approaches for solving this system of n equations in n variables. The three approaches are, the first one is algebraic approach. And in the algebraic approach, basically you take a system of equations, and in the algebraic approach you basically you're stuck with polynomials. Okay, you're solving a polynomial system of equations, and the first thing you do is to transform this system of polynomials f1 to fn into, let's say, a triangular system, or something that's nice, but triangular is almost the global default. There's other things that people have introduced. So triangular system is, say, g1 to gn, and gi is a polynomial in the first I variables only. So that's a triangular system. And then once you have done this, you say, well, solve it numerically. You solve the univariate polynomial for x1, and for each value of x1, you plug in here and solve for x2 and so on. Right? So it's almost...
How does the substitution work?
Right. And that's a very good point because people usually don't talk about that. And very often, well, you can approximate the roots here, isolate the roots here, and then of course, the isolation will give you approximations. You put approximate values here. And how accurate do you have to be in here in order to make sure you can correctly isolate here? So I think our paper in the last ISAC was one of the first methods that actually allows you to do this. Before that, people usually talk about root isolation for the integer case or something like that, but then you're helpless when you go into the next level because now this variable is algebraic numbers. So you cannot get that exactly. You could, but that would be so complex, nobody would ever want to implement that as far as I know. So you have to talk about approximations here. And at the nth level, all these are approximations except for this one. How do you know? You haven't changed the root structure and all those things. So that is usually silent, actually. And we have certainly no idea about what the complexity really should be. So this numerical part is actually usually, people talk about, do this, it's purely algebra. Okay, you use Grobner basis, or you can use other techniques like that. Okay. So that's the algebraic approach. Another approach is homotopy continuation. So you find initial solutions to some related system, and then you try to, from those roots, you try to homotopy yourself to the actual solutions of this guy. So in order to set up the initial system correctly, there's a lot of progress in the last few years on what is called a polyhedral method, which exploits the sparsity of your input system. And in higher dimensions, you have to exploit sparsity because the number of variables blow up in your face if you only look at the total degree and total number of variables. It's exponential in the number of variables, so you can't afford to do sparsity. So there's a lot of interest in this. And then how do you certify this? By Newton method. And really, all this is far from practical. I mean, the best known, one of the best known software here, Bertini, it's not certified. I mean, most of the time it works, but it doesn't, it can fail quite easily, actually. And the third method, which is subdivision, and this is what this talk is about, we want to find roots in the region of interest, V0. So you say, well, if I want to find all the roots, well, typically, very often you actually can define a big enough region that contain all the roots. So this is without loss of generality. But on the other hand, many applications, you know that you're only interested in roots in a very small locality. You know this in geometry, very often that's the case. In which case, this is actually very powerful, very useful. And if you're talking a polynomial case, people usually exploit Bernstein representation. And I'm going to talk a little bit more about these 4 papers. They're all using the Bernstein representation. And then in the analytic setting, typically people exploit Newton-like methods like Moore, Kravchik, or Hansen and Gupta, all of which provide methods to solve such problems, subdivision problems. So from now on, I'm going to stick to subdivision. Now, the challenges in solving multivariate system is that fundamentally this is an exponential problem. If the total degree of your polynomials is d, and there are n variables, is basically exponential. So how to avoid this? And in the polyhedral method, you exploit sparsity. You look at the sparsity structure of your polynomials. And in our case, subdivision, we exploit locality. The region of interest where you do subdivision, that's the region of interest. And that helps you to avoid this worst case exponential. You never want to find all the roots in higher dimensions. Yes?
So when you work, so you're given a system, do you work directly with that system or do you do some algebraic pre-processing?
I just don't like algebraic manipulation. So I try to avoid it as much as possible. And actually in our work, no. We work directly with the system. So when people give you systems in the multivariate setting, it's usually quite sparse and manageable, actually. And if you can avoid manipulating it using Grobner basis and things like that, you're way ahead of the game. That's my feeling. this has not been implemented, I don't know, but I have strong sense that this is the right way to do in high dimensions. Okay, so yes. By the way, Alexei, thank you for your questions. Because feel free to ask questions, okay? This is informal and will slow me down also. If anything I say is not too clear. Okay, so we have to avoid exponential behavior. An effectivity issue, basically we don't know how to, if you describe an algorithm in the real RAM model using exact real number operations, we have no idea how to actually effectively specify precision for the approximation all the way at every step. It's a very difficult problem. And 90% of the algorithms out there in the real world is actually not effective in this sense. When people implement it, they just wing it. They just do some epsilon thing and hope for the best, but it doesn't guarantee the correct structure actually, not at all. We want to solve this problem. And finally, complexity analysis. Well, if you're doing algebraic problems with polynomial systems, solving polynomial equations, yeah, you can count number of algebraic operations, no problem. But if you're dealing with analytic setting, where you have non-polynomial setting, well, you can't count those things. How do you do complexity analysis? And the basic idea is that it has to be based on the local geometry of the roots. And we'll do some of that analysis in this work, yeah.
So this mentions complexity analysis as a challenge.
Yes.
And is this complexity analysis of the worst case or some average case is a challenge? Or what kind of thing?
Right. Well, fundamentally, actually complexity analysis, in some sense, it's usually we don't really know very much of what to expect. What's the correct complexity we should expect? I mean, the only case we really understand is the univariate case, where we have this idea of a near optimality. And if the polynomial is integer coefficients, and you want to find all the roots. Other than that, what's the, how do you say something is near optimal? We really don't have any idea. Higher dimensions, forget it. You're happy to get any amount of data coming out from our analysis. So I don't know if that answers your question.
So are we saying that it would be great to have any kind of analysis because we don't have any?
Yes. Hopefully it will become, analysis is to help us understand what to expect, whether it's good or bad, right? And worst case complexity analysis is helpful to some extent, but that's not the whole story. And we don't know how to do adaptive complexity analysis, not very much. There's some ideas out there, something that I call continuous amortization, for instance, and try to link that to something inherent, say relate that to the integral of something related. That gives you some idea. So this is very new, not too much is known there.
Is there at least some number of benchmark tests with tables of how many seconds?
Yeah, at this point, I think one has to do, these are actually very practical things. One really ought to implement them and compare.
So they have not been implemented, that's what you're saying.
Our paper has not yet been implemented. Actually, there is a two-dimensional implementation, but we have changed the algorithm. So the version that I'm describing here has not been implemented, even in 2D. But in 2 or 3D already is very useful, because a lot of applications are 2 and 3D. So that I'm hoping to do. And people here who are interested, talk to me. I want.
So 3D meaning 2 variables?
2 variables or 3 variables.
But in Grosvenor basis are not expected to be bad, right?
That's right. But Grosvenor basis will take you so far, right? Grosvenor basis will take you to triangular system. And note, for an engineer, that's useless. Not yet. You have to do the last mile. You have to get approximations. You have to get, you cannot do it symbolically. That's not the last mile.
Right.
And that, people have done a lot of that symbolic part. That's, in a way, almost the easy part. It's the numerical part that we don't really have good ideas about what's the best, I think. Is it okay? Okay. So in this talk, I'm going to talk about an effective subdivision algorithm for this problem. I'm just defining the problem exactly. So root isolation, I call it root isolation problem for a system F. Bold letter means it's a vector. So bold letter F is F1 to Fn. And each of them are n variate. So it's a square system. And the B0 is a box in Rd, Rn. And we assume they're only simple isolated roots. So this is a zero-dimensional case. Simple isolated zeros in here, isolate them. So we have to output a set of boxes B1 to Bm of pairwise disjoint. They have to be disjoint so you don't duplicate the count of the roots. And each one contains exactly one root. Okay? And furthermore, you want to make sure that these roots, the zeros in this B1, in these boxes, actually contain all the roots which are in their region of interest in this B0, box 0. But notice that we might output accidentally roots which are slightly more in 2B, let's say. We can easily replace this 2 by 1 plus epsilon if that's of concern, but usually we're not too worried about that. So why do we need this fuss factor? Why don't I say the set of roots that I compute should be exactly equal to the roots in B0? Why is that? And this is a very important point. Actually, it's impossible to do in this general setting. In this general setting of functions. Even in the case of polynomials, it will be very expensive because it will require knowing, is this root really on the boundary? And in the case of polynomials, yeah, you can decide it. You can make what you compute to be exactly equal to the roots in B0. But in the analytic case, we cannot solve that problem. That's a zero problem that we cannot solve in general. So we have to fudge a little bit. Is that okay? Okay, now this is just a bit about the history behind this problem. I'm mostly focusing on the subdivision methods. Well, only subdivision. Huh?
I couldn't understand the inclusion. Do you mind showing it again?
Okay.
Is this right?
Yeah, so you output a set of isolating boxes. So they're exactly M roots. And these M roots should cover all the roots which are in your region of interest.
But the other one, I'm sure that.
But you might get roots which are just slightly outside, for instance, but not too far away. It's in 2B, 2B0. You have the initial box B0, a region of interest, and you double it, and you say, I'm not going to accidentally get anything outside of this 2B.
This is in it has all of the roots.
It's contained in here. Any root I compute must be inside this 2B.
But this doesn't have other roots.
Well, this 2B might have other roots. I'm not really interested in roots in 2B, but I'm really interested in roots in B0, not 2B0.
So it's like
Huh?
you have your output B1 to Bm,
Mm-hmm.
and they are isolating.
Yeah.
But like this B1 to Bm might go outside B0.
That's right. That's
But
right.
they won't go beyond 2B.
But won't go beyond.
That's
Won't go
what
too
it's-
far. Yeah.
Sorry, I got mixed up. B0 is special.
B0 is the input. It's the input region of interest. Okay. Okay. Good.
And M, is it M a part of the input?
No, not part of it. It's the number. It's just an upper bound on the number of roots in here. Because you have to get all the roots in here, so the roots in here cannot be more than M because we must get every root in this here.
And are there any restrictions on B0? Will it be
No.
everything?
Well, this is a strong assumption that B0 only has simple roots in here. Actually, 2B0, I should say there are only 2B0, because things on the boundary can cause trouble, so you have to worry about that.
And how does that work with the customer who has a system?
Which is what?
I have a system and I don't know about B0, so which roots are simple roots and so on.
If you have a system, F,
I'm supposed to give you B0, but I don't know what B0 is.
oh,
With that restriction.
then maybe you want to find all roots.
So B0.
Well, if RF is actually not algebraic, you might have infinitely many roots, like sine of x, there are infinitely many roots. So you have to say I'm interested in roots in some region.
How do I know in advance that there are only simple roots over there?
Oh, no, this is an assumption. Then the algorithm breaks down. Yeah, we don't guarantee. There's always some conditional things. I mean, one can go and work harder and try to say, what will happen if I give you something that violates this assumption? Okay, I think you can try to do something that's reasonable, but it won't be so precise as what I'm stating here.
Is there a quick test to decide on only simple roots?
No. Well, no. Most applications seems to have that kind of assumptions, and if it doesn't fit that, you throw a curveball at the system, it's going to break down. I'm very interested in algorithms that are unconditional, right? In some sense, unconditional. You give me the input as long as it's well defined, I should be able to. But when you go beyond algebraic case in the analytic functions, it's much harder to do. I don't think it involves very deep problems of zeros and things like that. So we can't solve that. So I just, in case you are familiar with these names, these are well cited in this area, and all of these algorithms fail to isolate. In both ways, actually, they actually don't terminate unless you give it an epsilon and say terminate when your boxes is less than epsilon. So this, of course, the epsilon is artificial, and when you terminate, okay, you can terminate, but what are you getting at that point? We don't know. And the second thing is that all of them actually fail to be even isolating. When they stop, the output box may have no roots, or it may have more than one root. So our algorithm actually appears to be the first to avoid these problems. Yeah?
So in all these papers, do they highlight these two issues?
They are usually not so formal. They just say we are finding roots, that's all. They don't go into zero dimensional, they don't say all those things. And typically, they're happy if you stop when the box is so smaller than epsilon and you can't go any further. They just output and don't guarantee that this is isolating on. Can throw it away, they don't guarantee.
In other words, as a reader, suppose I open the paper, is it clear to me immediately that this...
Not unless you have the sharp eye and you're looking for these things, yeah. That's why you can produce all these papers and they cite each other. I mean, and it's clear that there's something fundamentally missing in our thinking about real algorithms, about a continuum in a real. This paper, for instance, actually, usually these people talk as if you can manipulate real numbers, which is nonsense, of course. This paper actually does talk about floating point numbers, but it's all mixed up a little bit. And one of the things that I want to emphasize in this paper is that I think there's a very nice pathway to do this systematically for subdivision algorithms. Because somehow, if you design a subdivision algorithm, in some sense, you already have most of the things done already. It's not, I don't know, I can't guarantee it's automatic, but I believe it's usually not that difficult to make it fully effective. actually something that you can actually implement and guarantee that it will be correct. Okay, what is new? So our technique is applicable to analytic functions. So anything that's like Bernstein representation, that's polynomial. Ours is effective, that means you actually can implement it. We have complexity analysis based on intrinsic geometry of the roots.
So how are the analytic functions presented?
Okay, I think, let me do a very quick answer. All your functions, f, of course there are n components, each of them has a box function or interval form, meaning that given any box, it can give you compute an output interval that is guaranteed to contain all the values, a range function, and it will converge. When the box goes to 0, the width of the box goes to 0, it will converge to that value. So that's the first thing. And then we also need all its partial derivatives. So you need these two box functions, which are evaluation functions. And typically, it's very easy to get. Very easy to get. There's no systematic study of that. We actually introduced this in our paper 2013 for the first time, saying this is really what we mean when we say compute analytic functions. The polynomials, everybody say, oh, okay, give me the set of coefficients. Okay, that's the representation is clear. But when you go to analytic functions like sines, cosines, okay, you can say, okay, these are elementary functions. We all understand them. I can assume we have ways to compute that. But typically, the analytic function, the compositions of these things, right? If you're solving PDEs and all these things, you have compositions of these things, but they all satisfy the property I need. So almost any realistic problem that you want to solve fits into this setting. So here's the ingredients that we need. So again, I'm assuming this real function Rn to Rn, a region of interest, which is this V0 box. And we want tests, usually I say C or conditions, which returns true or false on the box. And I need operators on the box, meaning I need operator to split the box into sub-boxes or to contract a box, okay? Actually, contraction is, I just say it in case you think about it, but we're going to mainly focus on subdivision. When you do Newton methods, this is very important. And I'm going to write N of B as a Newton operator, which given B returns another box. And this Newton type, there are many Newton type operators that's well known in the literature, Kravchik, Hansen, Sengupta, Moore, Nickel, and so on. And we can use these things to define the contract. And when you are in the Newton zone, actually contraction is super fast. So you actually need to combine these with subdivision, ultimately. But for our present purposes, we don't handle that. And then we need tests. I call tests, sometimes you can call it predicates, same thing. And tests are either true, false, and they are tests on boxes, B. And there are three kinds of tests that I want. C0 is the exclusion test, very fundamental. And if number sign B means the number of roots in B, exclusion test, if it succeeds, then we guarantee that it has no roots. But if it fails, actually, we don't guarantee that there are roots, actually, right? So the converse is not guaranteed. So it's what we call one-sided tests. And most tests, all the tests we do are one-sided. And that's very important. Otherwise, you can't really make this effective. An existence test, existence predicate, EC. If it succeeds, then I know that there is at least one root. Maybe there are 5 roots, I don't know, but at least one. Jacobian test, JC. If it succeeds, I know there's at most one root, okay? And if you combine these two, Jacobian test and existence test, if this is true and this is true, then you've isolated the root, right? So our goal is to isolate roots. So these two are together very useful. A Newton type operator is well known, can give you uniqueness as well as exclusion. But in our setting, we break it up into two cases. The uniqueness is broken up into two separate tests. And I think there are advantages to that, but we don't fully understand the difference at this point. So I'm not comparing to Newton method at all in this talk. I'm just mentioning that there is a relation and we don't understand these things. Okay, so the box operator, I say subdivide. When you take a box, you subdivide into sub-boxes. Say you return k boxes. Usually k is at least 2. You have to break it into at least 2 boxes. That's bisection, and typically people do that. Or you can have 2 to the n if you split into equal sizes. The problem with splitting into 2 is that the boxes, even if you begin with hypercubes where every dimension are equal, when you split into 2, it's no longer all dimensions equal. And that causes some problems. And contraction means you take the box and shrink it to something smaller, where hopefully, and if it's a valid operator, then you haven't lost any roots, and you know that the roots is contained in the shrunk. And you say this contraction succeeds if the width of the box of the result contracting is less than that. So here's a very simple isolation algorithm, generic, just based on these abstract operators. You begin with a cube with an initial box, and there's one main loop, that's it. While the cube is not empty, pop one of the boxes, check the C0 exclusion predicate. If this exclusion predicate succeeds, continue. Continue means go back to the pop and go back to the cube. That means that's equivalent to discarding the boxes. I'm not interested. No roots there. I can throw it away. Otherwise, you can check exists a root and at most one root. And if this succeeds, you output the box. Simple, right? You are interested in root isolation. And we continue. Otherwise, we try contraction. If the width of Newton operator intersect B is smaller than our original, you have contracted it. Then you put this contracted box. Oh, I put the wrong box. I should put the contracted box inside here and go back to the loop. And if that doesn't succeed, you subdivide into your children and put all of them back into the cube. Okay, so this is a very basic framework. It's very hard to escape from this framework. Well, there are lots of other things you can do. You can put inner loops in there and things like that to make it. In fact, we will see inner loop in our algorithm. Now, if that thing halts, then actually we know the output is correct, actually. Because we don't throw away any boxes that might contain roots, assuming all our predicates are doing the correct thing. The main thing is termination. It's not obvious that at all that it terminates. And in fact, I can give 2 reasons why you might not terminate. Nothing to do with what the nature of the test is, but just if you have roots on the boundary, you may not terminate. And contraction doesn't always work. You might contract by less, but this is easy to take care of. This we do by doubling the size of the box. But it is an outline. And in this paper, we're going to talk about existence testing based on what is called the Moore-Kostelitis MK test. I won't talk about contraction from now on, although in practice it's important. I didn't do any analysis of this. In practice, just add it to the thing. It might speed things up, but I don't claim anything about its complexity. And I assume all my boxes are hypercubes, all the same size. So when I subdivide, I have to produce 2 to the n children, right? I split in every dimension, bisection in every dimension. This is not very practical, I know. In practice, you want to do bisection, and then but you can complicate our proofs and handle that if you want. But for simplicity, I'm just let's talk about hypercubes. So I want to say how I see effectivity. As I said, effectivity is really a very serious problem. Most of the algorithms we have out there on real numbers and so are simply not effective. How to convert a mathematically complete algorithm into one that is implemented correctly? And here I'm referring, it's a classic example in my mind. Pan and Schoenhager, their work on univariate root isolation. We knew optimal algorithm for long time actually, but it's not. We still don't know how to implement it. It's an effectivity issue. In contrast, in the last few years, we started discovering subdivision algorithms, first in the real setting, and then for the complex setting, which are near optimal, theoretically. And then within a year or so of this discovery, we actually could implement them. So that is something that I think is worth a lot. Subdivision is worth a lot for this property. And what is the reason? Here's my top-level description. Subdivision methods contain a pathway to effectivity. Somehow it is there. And if you think hard about it, you'll get it. And partly this paper, we're trying to make this effective pathway more explicit so that in the future we can exploit this pathway. Is that? Okay, maybe I'll take the next slide to explain what I mean by that. So we can describe algorithms in many levels, right? Just now, in this algorithm that I've described, it's very abstract. I just say what kind of properties is this predicate, these three predicates, that's it. And subdivision, that's fairly easy to understand, that there's no numbers there. So this is an example of an abstract algorithm. And we can analyze this. Well, of course, I can't analyze this until I know what are the instantiation of these three predicates, right? But other than that, I should be able to analyze this. So very often people describe algorithms abstractly. They are mathematical, they involve the real numbers R. But good luck if you try to implement it or try to analyze it. Now, what interval people have gone is go one level down. They say, well, you can't do it. You have to approximate it, and you have to guarantee that what you get computed is correct. Give bounds. Okay, so you have the functions. You have interval forms of those functions, and I write box R for the set of intervals with endpoints, real numbers. So you come down to it's a lot more concrete, but it's still actually not enough because you still have intervals with real numbers as endpoints. So what we want is intervals with endpoints which are dyadic numbers, big floats. Granted, from here to here is usually a small step, okay? But it is still a step that you have to take if you implement. You have to know what to do. But in the subdivision framework, this step to here is actually not that hard. So I give an example of this exclusion test, C0B. Remember what the exclusion test does? If it succeeds, then it tells you there are no roots. If it fails, all bets are up. We don't worry about that for now. In the proof, we have to worry about it. In the complexity analysis, we do have to worry about it. But for correctness, we don't. Well, not correct, partial correctness. We don't have to worry about it. Okay, so the abstract level, level A, or the interval level, level I, or effective level. So I write C0, and by definition, C0 just means 0 is not in F evaluated on the box. Okay, what is F evaluated on the box? F evaluated on every point in the box will give you a set. And 0 is not in the set. That's it. It's mathematical, but nobody can compute this guy, right? In general. So we go to the next level. We say, okay, the interval level, I replace F by box of F. That's the interval level. And now we actually do have a lot of interval methods to do that. And again, 0 is not in there. And finally, we actually have to replace this box F by tilde box F, the effective version, where everything is actually double dyadic numbers. And these are the three levels. We usually understand things conceptually at this level, but if you try to directly analyze at this level, it would go crazy because it's too messy. Things down there are just too messy. So we need help to go down slowly at every step. And these three functions, f of b, this is the range function, it gives everything in the box B, is contained in box F. This is usually called the inclusion function. And then from here, you also want inclusion. And if you have this inclusion function, then our predicates imply the opposite direction. The effective exclusion predicate, if it succeeds, tells you that interval version succeeds, and the interval predicate test succeed tells you that the abstract test actually succeeds. Okay? So we want to control these directions. So our algorithm, in summary, our algorithms and analysis, both, we always begin with the abstract level. We have to understand what abstractly is going on. And then we prove the correctness and complexity at this abstract level. And then we try to map it into the lower levels, into the effective interval level and into effective level. And ultimately, our correctness and complexity result must be about this level. This is really what matters. It doesn't matter what the abstract level is, really, right? But so we have to get down to that level. And usually people don't get down to this level. They might stop here, but not to the next level. Nice thing about this is it forces you to think very systematically. And at each level, you introduce new levels, new concerns, which are somehow more manageable because things are well under control. You know what's going on. Okay, so let me talk about the Miranda test. Okay, here, I think I'm running out of time, right? Yeah, so these are interval things. I'm not going to, these are preliminary. I just want to say, what's the Miranda test? The Miranda test in 2 dimensions, let's forget about higher dimensions, is if you have a box, you have 4 edges or faces. The faces come in pairs. There's one pair B1 plus and B1 minus, this pair and this pair, and another pair B1, B2 plus and B2 minus. And the simple Miranda test says, well, if the minus case, if the function evaluated on this edge is negative, on the negative edge, minus means less than 0, and the plus means greater than 0. And similarly, this, the plus edge, if it's positive and it's negative, Miranda's test passed. And Miranda's theorem tells you there exists at least one root. So this is a very famous theorem of Miranda, 1940, or sometimes called Poincaré-Miranda.
So it's not Miranda from Miranda Warning, it's a different thing.
Miranda what?
No, that's not. You can stay silent and so on.
Oh, Miranda. Okay, no, I don't think so. I don't think so. This is Italian mathematician, 1940. So Poincaré conjectured it, but Poincaré didn't prove it, and then he proved it. And it basically by reducing it to the Brouwer fixed point theorem, in some sense. I think it's equivalent. Okay, so that's a simple Miranda test. And I want to mention that this is one-sided. And there are other things which we don't want to talk about. Now, what we need is that Miranda test is not good enough. It doesn't always succeed. For instance, if you have 2 straight lines intersecting, there's a root at the intersection in 2 dimensions. Miranda test will never pass if the 2 lines has, let's say, an angle less than, say, 45 degrees between them. You can keep splitting and you'll never succeed. So this is just a linear case. So Kostelides noted that you have to do a preconditioning. So here is the precondition test that I call MK test. It returns true if the number of roots is at least 1. If it returns true, then you can say that it's at least 1 root, not the other way around. First of all, you check return false if the Jacobian matrix evaluated at the midpoint of the box is singular. Now, this is actually very dangerous. This is what I call a zero problem. Actually, if you have to do this, you're in trouble, actually. I mean, not in trouble, you have to work a bit harder to get this effective, actually. But you'll see that we somehow managed to sidestep this problem. And if it is it is not singular, then you compute its inverse, and you multiply the inverse matrix with F. So you transform F, and you get a new system, G1 to Gn, and this is what we call bulk G. And now you apply the simple Miranda test to this preconditioned system. But notice that we actually apply on the box twice the size, because roots on the boundary of boxes are an issue. It's a problem if you don't take care of this. So we double the box. So this is what we call the MK test. Okay, I won't talk about this. So I have to talk about two other tests. The exclusion test. This is fairly easy. 0 is not in Fi of B for some I. If 0 is not in there, then there cannot be any root. And Jacobian test, this is actually a very tricky one. You take the Jacobian matrix evaluated on 3B, and then now you have a matrix of whose entries are all intervals. And then you take the determinant of this interval matrix, and you check whether 0 is in there or not. So this is actually very expensive, and I'm very interested to make this efficient, because I suspect this will be a bottleneck in general. So now I have an abstract Miranda algorithm. There's an output Q called P, initialized to empty. There's a priority Q. Notice this priority, meaning that I want to, the Q is initialized to the box B0. And then, as usual, we have an outer loop. While the Q is not empty, remove the biggest box. And I can do biggest because this is a priority Q. And if C0 succeeds, you can throw it away. If Jacobian test succeeds, then we start a new Q. Because if the Jacobian test succeeds, there's at most one root. Now we want to go in and look for that root in the inner loop. So we start a new Q prime with the box B, and while this box is not this Q is not empty, we keep doing this until the Q is empty. Then we have thrown away everything. And otherwise, we subdivide and put everything back into the Q after you subdivide it and repeat. Okay? So it's quite similar to the simple one, except for this inner loop. And doing this as outside, so inside here we're going to do the Miranda test. And that actually saves us a lot of trouble. And here's the outer loop, and the inner loop is really this part. Remember, we initialize the Q to the box you found, that you know there's a root there, and we pop it. And then, this is the initial case, don't worry about that. And if it fails, then, if it succeeds, then we throw it away. In some sense, we push, we continue. Otherwise, we go into testing for the more crystallized test. If it succeeds, now we know this definitely contains a root. We put it in the output Q. This P is the output Q. We add this. And this says that we can discard from Q all the boxes that actually is contained in 3B. So this is a very simple way to clean things up. So these numbers are chosen carefully, 3B, 2B, so that things are very simple to implement. So I've described an abstract algorithm. So this is Miranda. I want the interval version, box Miranda. I want the effective version, which is this one. And all you have to do is replace MK by box MK, and box MK by effective MK. And similarly for exclusion and Jacobian. And inside these tests, if they are interval methods, well, you use interval methods. I mean, if they are range function, you use them. Unless you run into trouble like deciding zero, that matrix is non-singular. You have to worry about that. That's a difficult problem. But fortunately, we structured our algorithm that we don't worry about that. Now the analysis, this is going to get messy. But remember, I want to do everything first by understanding what's happening in the abstract case first. If I understand that, then I can say, can I transfer it to that level? What else appears there? And what happens when you move from here to here, what will happen is that something like Lipschitz constant will come into play. And when you go from here to here, usually you just make sure that the approximation is proportional to the size of your box, width of your box. Do it properly, then you can go all the way down. Okay. How much time do I have? 5 minutes. Okay. I'm going to run through that. So there's some kind of condition number going on in the abstract thing, and then we try to define certain condition number and define lambda to be the smallest root such that certain equation holds, and then we prove that if the root is simple root, then what we define makes sense. And the first theorem says that, well, if you have a box B that contains this root, this simple root, and if the width is small enough, then the precondition system is actually well defined. And furthermore, this is bigger than something related to the width. This is smaller than minus something related to the width. In other words, you can actually approximate it and detect it by effective methods. We actually made a mistake in our several years, about 5 years ago, I wrote a paper with colleagues, and actually we missed some of this detail. We only did abstract, we have a correct abstract algorithm, but at the interval level, we missed this detail, and that's wrong. You need this extra, buffer zone. And then when you go to the interval level, you have to start looking at Lipschitz constants. And then you have the interval analog of this lambda. And then you have a corresponding theorem that tells you that the box function, the interval version, will succeed. You see, this is really doing the converse. Yeah? I said the tests are always one-sided. If it succeeds, you know something. If it fails, you know nothing. But the partial, these kinds of theorems are actually converses. They say that when will you're guaranteed to succeed. If there's a root and certain other condition, you will succeed. So it's a converse, but partial. And the Jacobian test, you can do something similar. It turns out that to analyze the exclusion test, you need a different treatment. And again, you get different constants. So in conclusion, I say that we have provided a complete algorithm for isolating simple roots. It's effective. And I think this idea of 3 levels of description is very useful. And hopefully will make a lot more algorithms that people have studied more actually effective and actually implementable. So limitations of current work, we have preliminary implementation for 2-dimensional case. Empirical work is needed to compare against Newton method. Newton type methods actually can give you effective methods as well, but that has not been analyzed like we have. Usually people talk about this at the abstract level. They don't go down to it. And the broader view is that multivariate systems remain very challenging, and complete and analytic numerical algorithms are rare because people don't get effective. And finally, we need good computational models for such developments. So I'll stop here. Thank you. What's that? Yes.
Do you have some small example that would illustrate concrete steps of your algorithm?
Each step of my algorithm. The predicates, I guess. You want predicate? Something?
Well, whatever you could give. So ideally, maybe a system you mentioned two variables, and then in the end also.
Right.
What do
My co-author Joanne, she's working on implementations. We have an old version of it where things are less clear, because as I said, this idea of making things effective is something that I'm forced to think about it if I want to make. And previously we never think about that too carefully. Like everybody else, we have this blind side of things. So I'm afraid
Not yet.
not yet. Yeah.
So how many subdivisions are typical, for an example?
Right. No, I don't know. Well, these are all bounded in terms of certain parameters, this lambda, which are all root bounds and things like that. And if your roots are very close, the lambda can be very small. So that you're forced to do a lot of things. So the analysis is just very preliminary, very preliminary. I mean, it's already not trivial, but it is. I think it will take another 5-6 years of hammering this to really get something that we really is clean. Because if analysis is dirty, nobody cares to read it. Really, you want things which have insights, right? I mean, analysis is to provide insights. Actually, the results itself is thrown away in some sense. We have to learn the techniques and get the insight, and we need to develop clean methodologies for doing this. And I would say that we don't have many good examples. Unless you do algebraic count how many operations, right? But here there is subdivision, and that's not something you can do. You can't count number of arithmetic steps. That alone doesn't work. You need something continuous. And yeah, so I would say, like many areas, really you ought to implement and see that it works well, that it can solve the problems that people are interested in. And there are lots of examples in the literature people have accumulated, and one should try and implement them. Does it answer your question?
So there might not be a very small example.
We certainly have done 2D cases where we do curves and surfaces and things like that, and it works, because what arises in normal applications are not weird things. They don't even have multiple roots and things like that. So things are all going to be quite well defined. It's only in the rare cases, all these algorithms are so difficult or so complex because we're trying to catch all possibilities, and we pay a lot of price for being complete, right? Otherwise, you say, oh, generically, I can ignore all these boundary cases, which is what usually. Okay. Any other questions? No. Okay. Thank you. So I have a copy of this paper if anyone is interested.